Observe the same material in two states. Left, matter at its coldest limit is completely static. Right, molecules are in violent motion. This microscopic kinetic energy is what we identify as temperature. We measure the intensity of this motion using the Kelvin scale, the standard for all thermodynamic calculations. If we were to remove all possible kinetic energy, we would reach absolute zero, 0 Kelvin, or negative 273.15 degrees Celsius. At this point, all molecular vibration stops. We link these microscopic states to our macroscopic world through the ideal gas equation. Here, absolute temperature directly dictates the pressure and volume of a system based on its molar quantity. But temperature is merely a measurement of state. When energy moves from a higher temperature body to a lower temperature body, we define that energy in transit as heat. It is a common misconception that objects store heat. In reality, they store internal energy. Heat is only the act of that energy moving across a gradient. In this video, we will track this energy transfer through a unified mathematical model, observing how it forces materials to expand, absorb energy, and eventually change their physical state. As thermal energy enters a solid, the increased kinetic energy of the molecules forces them to take up more space, causing physical dimensions to expand. For a railway track, length change is proportional to original length, temperature increase, and the linear expansion coefficient. In 3 dimensions, the volume coefficient is 3 times as large. Prevent this expansion with rigid constraints, and thermal stress develops based on Young's modulus. This is why engineers include expansion joints in bridges and pipelines. Without a designated gap for this movement, the internal stress would buckle the entire structure. Most matter expands predictably when heated, but liquid water presents a critical exception to this rule. Between 0 and 4 degrees Celsius, water actually contracts as it is heated. It reaches its maximum density at exactly 4 degrees, becoming heavier than the colder water surrounding it. In a freezing lake, this 4-degree water sinks to the bottom, while the colder, less dense water rises to the surface and freezes. This creates a top-down freezing process. This anomaly is the specific mechanism that allows the depths of a lake to remain liquid, preserving aquatic life through the winter. Now that we have established the physical effects of expansion, we must account for the energy required to reach those temperatures. To do this, we use a heating curve, tracking temperature rise against a continuous supply of heat. The line's steepness represents specific heat capacity, the exact energy needed to raise 1 kilogram by 1 Kelvin. Water has an exceptionally high specific heat of 4,186 joules. This high inertia allows oceans to absorb massive amounts of solar radiation with only minimal changes in temperature, which stabilizes the climate in coastal regions. We calculate these thermal interactions through a process called calorimetry. In a closed system, the law of conservation of energy dictates that any heat lost by one substance must be gained by another. By balancing these gains and losses, we can precisely calculate the final equilibrium temperature when different substances are mixed. However, there are moments when adding heat fails to raise the temperature at all. At a melting or boiling point, the heating curve plateaus. Even as heat is added, the temperature remains constant. This is latent heat. This energy is spent entirely on breaking the intermolecular bonds holding the state of matter together. These transitions require a staggering amount of energy. Converting 1 kilogram of water into steam requires over 2 million joules, nearly 500 times the energy needed to raise its temperature by a single degree. This explains why steam causes much more severe burns than boiling water. Upon contact with skin, steam condenses and releases all of that stored latent heat at once. On a phase diagram, pressure and temperature map a substance's states. At the triple point, all 3 phases exist simultaneously. For water, this occurs at 273.16 Kelvin and 611 pascals. Here, ice, liquid, and vapor coexist in perfect balance. Heat is more than a way to change temperature. It is the energy required to physically reorganize a substance's molecular structure into a new state. Finally, we must look at the mechanics of how this energy moves across space, and the laws that govern its speed. In solids, heat moves through conduction. Energy is passed from molecule to molecule via vibrations, without the material itself moving. The transfer rate, h, is defined by the conduction equation. As a barrier's thickness increases, heat flow drops. Larger surface areas allow more energy through. Thermal conductivity, K, also dictates flow, being high for metals like copper, but low for insulators like wood. In liquids and gases, energy moves via convection. The heated fluid physically moves in bulk, creating the currents that drive our weather and ocean breezes. The third method is radiation. This is energy moving as electromagnetic waves, allowing heat to travel through the vacuum of space at the speed of light. But how quickly does an object lose this heat? Newton's law of cooling states heat loss is proportional to the temperature difference between an object and its surroundings. This creates an exponential decay. Cooling is rapid at first, but slows significantly as it approaches room temperature. Whether calculating the insulation of a building or the cooling of an engine, these gradients and geometries dictate the speed of thermal exchange. We have now built a complete model for thermal dynamics. We know that every interaction is driven by a temperature differential, forcing energy to move from high to low. This energy is absorbed according to a material's specific heat, which directly leads to its physical expansion. When that material reaches a critical threshold, the heat is redirected to overcome molecular bonds, resulting in a change of state. These formulas are not abstract concepts. They are the tools used to design radiators, insulation, and the high-pressure systems that power modern industry. By mastering these properties, we can accurately predict and control how matter will respond to the constant flow of thermal energy.